looking at starting 2.4 with the chain rule. Now, we haven't discussed the chain rule yet, and it is one of the most powerful differentiation rules that we have. Now, the rule deals with composite functions. Okay, so we're talking about functions within functions. And this is going to add a lot of versatility to all of the other rules that we've already learned. So let's look at a couple of examples. Things we can do without the chain rule. We can do x squared plus 1. That's no problem, right? It's a function plus a function. Sine x, that's just a trig function, no problem. 3x plus 2, another function plus a function. X plus tan x, just a function plus a function. We have the sum and difference rules. We can take care of that, no problem. Let's look over here. What about the square root of x squared plus 1? Problem. This is a function inside of another function, right? This is, we can think of this as being like f of g of x, right? Where f of x, the outer function, is the square root of x, and g of x is the x squared plus 1. So we have a function inside of another function. Same thing here. 6x is inside the sine function. Here, 3x plus 2 is inside of x to the 5th, right? We've got x plus tan x squared. The x is fine, but here we've got tan x squared. We've got a function inside of a trig function. So, before I lay out for you exactly what the chain rule is in terms of something you'll understand, let me put it in terms of something you may not quite grasp until we look at the next example. Chain rule tells us that if y is changing with a rate of change with respect to u, we're going to call it dy du. Now, u is a function of x. So u is changing du dx times as fast as x. So we can take the rate of change of u with respect to x. And y is changing totally dy du times du dx. So if we want to look at y, think about it like this. Y is some function of x. We're going to call g of x, we're just going to call it u, so that y equals f of u. So if we're looking for dy dx, we first have to take the derivative of y with respect to u. We have to take dy du. So we're going to take y with respect to u, and then we're going to take the derivative of u, which is gx, with respect to x, so du dx. If we multiply these things together, we'll get to dy. So this may not make a huge amount of sense, but let's look at an example. Here we've got a set of gears. Now notice the second and third gears are on the same axle. This is important. Now, as we turn axle 1, gear 1 turns gear 2, which in turn turns gear 3, which in turn turns gear 4. So axle 1 spins with respect to axle 2, but axle 2 spins with respect to axle 3. Can we figure out how axle 1 spins with respect to axle 3? So first thing we want to talk about is the fact that gear 1 has a radius of 1, gear 2 has a radius of 3, and we have gear 3 has a 1, and gear 4 has a 2. So all of these are going to come into play because the radius being different means that the circumference is different, right? And the circumference is how much we have to roll around. So as we go around one time, how much of this does it go around? Or if this goes around one full time, how many times did this have to go around? How many times did this go around? And if this one went around one time and this went around so many times, how many times did this one go around? That's what we're looking at, okay? So we're going to, in this case, we're going to let axle 1 be our y. So we're talking about y revolutions per minute. So we're spinning it at a rate of y revolutions per minute. Axle 2, we're going to call u. So this is going to be u revolutions per minute. And axle 3 is going to be x. So we're talking about x revolutions per minute. Now remember, we have shown, well, we haven't shown, we've stated that dy dx equals dy du times du dx. So we're going to find all of these things and see if this is true. Now, because that circumference of the second gear is 3 times that of the first, then that means that that first axle, if it spins 3 times, that should do 1 time on axle 2. So we're saying that, and the second axle makes 2 revolutions to turn the third axle once. So we can write this as dy du equals 3. So with respect to u, y turns 3 times. Y turns 3 times when u turns 1 time. So 3 over 1. And here we're going to say that u turns 2 times as x turns 1 time. Can we say that? Can we say when y, so remember this is y, this is u, and this is x. So when y turns 3 times, that gets me u once. Remember, we're always going to say it's going to take more turns of a small gear than a big gear. All right, and then we're going to go to u. So since u is 1 and x is 2 in terms of the circumference, then I know it's going to take me 2 times on u to get 1x. So this is where these are coming from. U turns twice for 1. So dy du is 3 and du dx is 2. So combining these two results, we know that if we turn the first axle, if we turn this 6 times, that made this go around twice. Okay? So this axle spent twice. If this axle does twice, this axle does once. So we can see, sure enough, 6 spins here gives us 1 spin here. So we know that that's the case. Can we prove now that if this and this come together for 6, that is what dy dx is? So dy dx is the rate of change of the first axle with respect to the third axle, right? So this is 1 with respect to 3. And we want to show that this is equal, not 1/3, first with third. So first turns, third turns. I don't want y'all to think that was 1/3. Now we want to show that it's the rate of change of the first axle with respect to the second axle. So we want to talk about this is du, first axle with respect to the second axle, dy du, times the second axle with respect to the third axle, du dx. Okay, so that's what we want to show. Well, we know dy du was 3 and du dx was 2 from previously, so that multiplies together gives us 6. So this should be the rate of change of the first axle with respect to the third axle. So in other words, the rate of change of y with respect to x is indeed the product of the rate of change of y with respect to u and the rate of change of u with respect to x. Now, if this didn't make a whole lot of sense, watch it again. See if you can kind of follow along with what we're talking about. And if you have a question about this one, I'm more than happy to work this out in class. But the important part is this. This is the chain rule. This is the part that we just talked about. If y is a function of u and u is a function of x, then the derivative of y with respect to x is going to be the derivative of y with respect to u times the derivative of u with respect to x. This still may not click in your brain. So what we want to show you is this part. If we look at it as being a function of a function, right? This is a composite function. Then I'm saying if we take the derivative of a composite function, we're going to take the derivative of f, and we're going to leave g alone. We're going to leave the inner function alone. We're only going to take the derivative of f, leaving the inner function g alone, but we're going to tack on the end times the derivative of g, that inner function, with respect to x. I'll show you what I'm talking about in just a second. So when we apply the chain rule, it's helpful to think about the composite function, right? F of g is having both an inner part and an outer part. And most of the time, the inner part is whatever you can write in parentheses, and the outer part is what's left if you take that inner part out and replace it with x. For example, square root of 2x plus 3. The inner function is the part that I could write in parentheses. So inner would be 2x plus 3. If I pull the 2x plus 3 out and leave just an x, then square root of x is my outer function. So what we're saying when we do this, the derivative of y, so if I look at the derivative of this, then it is just the derivative of the square root of x, leaving the inner function inside of it, times the derivative of the inner function, 2x plus 3. So it's really important that you be able to understand which part is the inner function, which part is the outer function. So let's look at a couple of examples and see if we can figure out how to decompose them. So here's our y. What's g? What's the inner function? Well, I could write the x plus 1 in parentheses, leaves me with 1 over, in this case, we're going to call it u. So if I take the x plus 1 out and make it u, then 1 over u is my outer function. What about y equals sine of 2x? Here, the 2x is the part that's in parentheses. If we pull it out and replace it with u, we get sine u. Square root of 3x squared minus x plus 1. So the part under the radical, that's our inner function, 3x squared minus x plus 1. Our outer function is just that square root. Here, tan squared x, the tan x is the part, because we kind of draw these weirdly. This is tan of x squared is what it means, right? So tan x is the part in parentheses, and the u squared is what's on the outside. So this is the chain rule. We haven't really used it for a huge amount of just base problems, you know, like here's a problem, take the derivative. Here's the problem, take the derivative. We're going to do that in the next section in the general power rule. This is just really a way for you to understand what's going on in the general power rule and how we actually, why it works when we do what the general power rule does. So if you have any questions about this, please ask questions in class or shoot me a reminder.